things on a small scale is so fantastic. It's so wonderfully different, so marvelously different than anything that behaves on a large scale. You say electrons act like waves. No, they don't exactly. They act like particles. No, they don't exactly. They act like a kind of a fog around the nucleus. No, they don't exactly.
Why does magic seem unreal? At the subatomic level, things weirder than magic happen all the time. This might seem like fantasy world, as Feynman put it, which I am going to read on the book. Because atomic behavior is so unlike ordinary experience, it is very difficult to get used to, and it appears peculiar and mysterious to everyone, both to the novice and to the experienced scientists. Even the experts do not understand it the way they would like to, and it is perfectly reasonable that they should not, because of direct human experience and of human nature applies to large objects. But we are not talking about the large objects. We are talking about things at the subatomic scale. This is where we enter the arena of quantum mechanics. Let's have some overview about the quantum mechanics. Quantum mechanics is a branch of physics that deals with the behavior of matter and energy at the atomic and subatomic scale. It has its roots in the early 20th century when physicists were struggling to explain the behavior of light and matter at the smallest scales. One of the earliest concepts in quantum mechanics was the wave-particle duality, which refers to the idea that particles can behave like waves and waves can behave like particles. This concept was first proposed by Louis de Broglie in 1924, who suggested that particles like electrons and protons could have wave-like properties. Later that year, experiments conducted by Davison and Germer confirmed the wave-like nature of electrons. And in 1927, Niels Bohr and Heisenberg developed the Copenhagen interpretation of quantum mechanics, which became the dominant view of the field for many years. This interpretation points that the behavior of particles is inherently uncertain, and that their properties cannot be known with complete accuracy. It also introduced the concept of wave function collapse, in which the act of observing a particle collapses its wave function and forces it to assume a specific state. Then in late 1920s and early 1930s, quantum mechanics was used to explain the structure of atoms and their spectra. Scientists like Erwin Schrödinger and Paul Dirac developed equations that describe the behavior of electrons in atoms, and these equations were used to predict the energy levels and spectral lines of different elements. In 1940s and 50s, physicists developed quantum field theory, which extended quantum mechanics to include the behavior of fields like electromagnetism and the strong and weak nuclear forces. This theory points that particles like electrons, protons are actually excitations of fields, and that interaction between the particles are mediated by these fields. The accumulation of many years of research in quantum field theory is the standard model of particle physics, which was developed in 1970s and 80s. This theory describes the behavior of particles and forces at the smallest scales, and includes the electromagnetic, strong and weak forces. It also includes the Higgs boson, which is responsible for giving particles mass. In conclusion, quantum mechanics has come a long way since its early days of wave-particle duality and the Copenhagen interpretation. With the development of quantum field theory and the standard model, scientists now have a robust framework for understanding the behavior of matter and energy at the smallest scales. Was Feynman right when he said, "If you think you understand quantum mechanics, but you really don't understand the quantum mechanics"? So here is my friend Murtaza Abbas. He will talk about the quantum physics, but in terms of the practical field. So Murtaza Abbas, I will request you to give this lecture in our own mother tongue.
Exactly. If we're going to quantum mechanics, which octave branch physics, so as insan and اَمِچ ڈِسکَوری کٔر ساینٹِسٹو تِم گٔے گۄڈٕ پٮ۪ٹھ واریاہ کَنفیوٗز تِکیازِ یہِ اوس چیلینج کَران سٲنۍ پرٛیٖویَس بِلیٖفٕس کہِ یُس اَسہِ ایٚکٕسپیٖریَنس چھُ وٲلڈٕ یُس أسۍ وٕچھان چھِ لارٕج سکیل آرڈرَس پٮ۪ٹھ اوس تِمَن سارنٕے چیٖزَن چیلینج کَران تہٕ ییٚلہِ کٲنٛسہِ تہِ اَتھ سۭتۍ گۄڈنٮ۪تھ چھِ یہِ گژھان سُہ چھُ واریاہ پریشان گژھان پَزٕل گژھان کہِ یِم چیٖز کِتھ پٲٹھۍ چھِ کٲم کَران سون موٹِو چھُنہٕ کہِ أسۍ ہٮ۪کو یہِ پوٗرٕ پٲٹھۍ اَنڈَرسٹینٛڈ کٔرِتھ مگر کُنہِ حدَس تانۍ ہیٚکہِ کٕلیر گٔژھِتھ سورُے کہِ یہِ کِتھ پٲٹھۍ چھُ گژھان تاکہِ تھوڑا بہت گژھِ بیٹَر اَنڈَرسٹینٛڈِنٛگ اَمہِ سَبجَکٹٕچ تہٕ یُس اَسہِ تھیورِٹِکَل نالیج چھِ سۄ گژھِ کَمپلِمٮ۪نٛٹ تہٕ اگر أسۍ کوانٹَم فِزِکٕس چھِ یَژھان اَنڈَرسٹینٛڈ کَرُن أسۍ کَرو سٹاٹ یُس اَسہِ ساروی کھۄتہٕ بیسِک ایٚکٕسپیرِمٮ۪نٛٹ چھُ سُہ گوٚو ویو پاٹِکَل ڈُویلِٹی منٛز یِم ایٚکٕسپیرِمٮ۪نٛٹ چھِ أسۍ ہٮ۪کان کٔرِتھ تہٕ ساروی کھۄتہٕ گۄڈنٮ۪تھ وٕچھو أسۍ ویو چھِ کیٛاہ ییٚتٮ۪تھ چھُ اَسہِ اَکھ سِمپٕل یہِ ٹَب اَکھ سٮ۪ٹ اَپ ییٚتٮ۪تھ تھوٚمُت تہٕ یُتھُے أسۍ اَتھ منٛز ڈِسٹٔربَنس چھُ کَران کِرٛیٹ یہِ چھِ یہِ ڈِسٹٔربَنس پویِنٛٹ اے ٹُو پویِنٛٹ بی واتان تہٕ اَتھ ڈِسٹٔربَنسہِ چھِ ویو وَنان یہِ چھِ اَسہِ ویوٕچ ساروی کھۄتہٕ بیسِک ڈِسکرٛپشَن یُس اَسہِ گۄڈٕ پٮ۪ٹھ چھِ آمٕژ دِنہٕ تہٕ وۄنۍ اگر أسۍ یہِ أتھی تھاوو أسۍ تُلو یہِ چھِ 9 وولٹ بیٹری مےٚ اَتھَس کٮ۪تھ بیٚیہِ چھِ یہِ پایزو اِلیکٹِرٛک بَزَر ییٚلہِ أسۍ یہِ کَنٮ۪کٹ چھِ کَران اَتھ چھِ نیران ساوُنٛڈ ویو تہٕ یہِ تہِ چھِ اَکھ ویو بِلکُل تہٕ وۄنۍ اگر أسۍ ییٚتٮ۪تھ یُس لیزَر چھِ اَسہِ یُس کوانٹَم میکینِکس چھُ وَنان کہِ یۄس یہِ لیزَر چھِ یُس یہِ لایٹ چھِ اَتھ چھِ اَکھ ویو لایک پرٛاپَرٹی یہِ چھِ کوانٹَم میکینِکسُک داو چھُ یی تہٕ اَسہِ چھُ وۄنۍ وٕچھُن کہِ یۄس یہِ ویو یا یہِ ویو چھِ اَتھ تہٕ یۄس یہِ ویو چھِ یۄس ییٚمہِ نِش واریاہ الگ چھِ باسان اَتھ کیٛاہ سِمِلیرِٹی چھِ یہِ چھُ سون لایٹ ویو بِلکُل اَتھ کیٛاہ سِمِلیرِٹی چھِ تہٕ یہِ چھُ سون گول یَتھ منٛز ییٚمہِ خٲطرٕ أسۍ کَرو ساروی کھۄتہٕ گۄڈنٮ۪تھ ینٛگٕز ڈبل سِلِٹ ایٚکٕسپیرِمٮ۪نٛٹ ینٛگٕز ڈبل سِلِٹ ایٚکٕسپیرِمٮ۪نٛٹ یہِ چھُ اَکھ سُہ ایٚکٕسپیرِمٮ۪نٛٹ ییٚمۍ کوانٹَم میکینِکسٕچ بُنیاد ترٛٲو سون دُنیٲیی تجرُبہٕ چھُ اَسہِ یہِ وَنان کہِ اگر أسۍ لایٹ ترٛاوو دۄیو سِلِٹسو کِنۍ یِم تِم تَنہِ کھرٛٮ۪پہٕ ہِش چھِ آسان یَتھ أسۍ سِلِٹٕس چھِ وَنان اگر أسۍ لایٹ تَپٲرۍ کِنۍ ترٛاوو سون تجرُبہٕ چھُ یہِ وَنان کہِ اَسہِ یِن 2 علیحدٕ پویِنٛٹٕس یا ڈاٹٕس اَتھِ مگر ییٚلہِ أسۍ ایٚکٕسپیرِمٮ۪نٛٹ بیٚہوان چھِ کَرنہِ اَتہِ چھِ أسۍ اَکھ پیٹٲرن وٕچھان یَتھ أسۍ ڈِفرٛیکشَن پیٹٲرن وَنان چھِ کوانٹَم میکینِکس چھُ اَکھ اہم داوٕ کَران کہِ اَکھ لایٹ رے چھِ ویو پرٛاپَرٹیٖز ہاوان تہٕ ساروی کھۄتہٕ برونٛہہ وٕچھو أسۍ کہِ ویو کیٛاہ برتاو چھِ ہاوان ڈبل سِلِٹ ایٚکٕسپیرِمٮ۪نٛٹَس منٛز أسۍ نِمو اَکھ ٹرٛے تہٕ أسۍ بَرو یہِ آبہٕ سۭتۍ تہٕ پَتہٕ وٕچھو ییٚلہِ یہِ ویو ڈبل سِلِٹ منٛز نیرِ تہٕ کیٛاہ برتاو ہاوِ أسۍ چھِ وٕچھان کہِ ییٚلہِ یہِ ویو اَمہِ منٛز گُزران چھِ اَتہِ چھِ اَکھ برتاو یِوان لَبنہٕ یَتھ أسۍ ڈِفرٛیکشَن پیٹٲرن چھِ وَنان اَتھ منٛز چھِ کرٛٮ۪سٹ تہٕ ٹرٛاس لَبنہٕ یِوان ییٚمہِ سۭتۍ چھُ اَسہِ اَندازٕ گژھان کہِ اَکھ ویو کیٛاہ برتاو گژھِ ہاوٕنۍ ڈبل سِلِٹ ایٚکٕسپیرِمٮ۪نٛٹَس منٛز وۄنۍ وٕچھو أسۍ کہِ اَکھ لایٹ ویو کیٛاہ برتاو ہاوِ यह तजुर्बह शुरू करने ब्रोह जरूरी इंतबा यह लेजर अ खतरनाक हिस्सा यम तजुर्बच सेफ्टी ग्लास वरै यह तजुर्ब करन हेक अछन नुकसान वातनयित सारी खुद गोडनेथ करो अख सब्ज लेजर इस्तेमाल गोडनेथ करो लेजर नॉर्मली पॉइंट वुचान कि अत कहीं गसान अत टोटल अख स्पॉट अत मगर यम विज अख डबल स्लिट अनान अत अजीबो गरीब बर्ताव वजूदस मज वुचान कि अत छिट छकरन निवान बराबर तिथे पे अम ब्रोह वाटर वेव्सन सत वुच तो यम सत लाइट हुंद वेव नेचर साबित गसान वन वुचान कि यमन दोन स्पॉटन मजबाग दूरी यह क्या हेक वन यमन दोन मजबाग दूरी यथ फ्रिंज विड्थ वनान यह तो इक्वेशन अत दिथ यानी W = लैम्डा मल्टीप्लाइड बाय D डिवाइडेड बाय S वनान कि अस हेको अम इन्फॉर्मेशन सत्या कह लाइट मुतलिक तो अत स्लिट अत मुतलिक इन्फॉर्मेशन कड़ित यह यंग्स डबल स्लिट एक्सपेरिमेंट तो अम पत वुचो कि यह कूता फायदेमंद छु
Here we are going to see the practical application of the phenomenon of diffraction by measuring the thickness of a pashmina thread. We can also use a strand of hair or we can use a thin metal wire. The thread that we are going to use here has a thickness of around 15 micrometers. So this thickness is on the order of the wavelength of visible light. So when a laser beam hits the thread, it's going to produce a very distinct diffraction pattern on the screen. So that pattern consists of maxima and minima, and by measuring the distance between two adjacent maxima and minima, we can measure the thickness of the diffracting object, which in this case is the pashmina thread. So let us now properly see how we get to know the diameter of the pashmina thread. We will use the same setup that we previously used to do our double slit experiment. All of the setup is same except for the fact that we are now using a pashmina thread. The screen is placed at a distance of 34 centimeters from the setup, and the green laser that we are using here has a wavelength of 532 nanometers. When this laser hits the thread, we observe this pattern of bright and dark spots called the fringes. We are going to mark these bright spots and find the distance between the center of the brightest spot to the first dark spot. This will give us the fringe width. Now we are going to perform proper calculations to find the thickness of the pashmina thread. So we have the formula: thickness of the diffracting object, that is the small d, is equal to lambda d by y, where lambda is the wavelength of the laser used, d is the distance between the screen and the thread, and y is the fringe width. Now putting all the values in the formula, wavelength lambda is 532 nanometers, and the distance between the thread and the screen, that is the d, is 34 centimeters, and our fringe width that we measured to be around 1.2 centimeters. Doing the calculations, we get the thickness of the pashmina thread as 15.1 micrometers. This is called Babinet's principle, one of the thousands of principles used by quantum physicists all around the globe. Quantum mechanics has a broad range of applications, from cryptography to explaining the structure of the DNA. Quantum mechanics is the future.
Let us see the other side of the quantum mechanics. Traditional biology has mainly focused on classical mechanism and biochemistry to explain the different processes which takes place inside the human cells. But recent advances in the quantum physics have revealed that certain biological phenomena cannot be fully understood without considering the principles of the quantum physics. So let's take an example of exchange of information. and the chemical reactions which take place inside the living cells. There are tens of thousands of chemical reactions which takes place inside the living cell within a minute. So for example, we say there are 10,000 reactions which take place in a minute inside the cell. So that 10,000 different chemical reactions which take place inside the cells need 10,000 different pHs. How is it possible? How enzymes work to make the reactions achievable, which may take tens of thousands of years to happen? And how do complicated signaling process and the transference of information take place within the cells? Here, the quantum physics comes for the rescue. For a decade, quantum biology is a fascinating and rapidly evolving interdisciplinary field that explores the role of quantum mechanics in biological processes. It aims to understand how quantum phenomena, which are usually associated with the behavior of subatomic particles, can influence and play a vital role in the functioning of living organisms. Some of the key concepts in quantum biology which needs attention are quantum coherence, quantum tunneling, quantum entanglement, photosynthesis, brain functioning, and more. Quantum biology is a relatively young field, and there is still much more to explore and understand. As researchers dig deep into the quantum nature of biological systems, they hope to gain insights that could lead to revolutionary advancement in various fields, from medicine and biotechnology to material science and beyond.
So this was the part 1 of our series on quantum mechanics. Stay tuned for more, and if you want to join us, please contact us on the email down below.